This section focuses on establishing a single switch network as part of enterprise network expansion. The introduction of a switching device as part of the enterprise network demonstrates how networks are able to expand beyond point-to-point connections and shared networks in which collisions may occur. The behavior of the enterprise switch when introduced to the local area network is detailed, along with an understanding of the handling of unicast and broadcast type frames to demonstrate how switches enable networks to overcome the performance obstacles of shared networks. So upon completion of this section, it is generally expected that trainees will be able to explain the decision-making process of a link layer switch, as well as configure parameters for negotiation on a link layer switch. Until now, we have focused on networks that involve a minimal number of end stations operating in either a shared or a point-to-point form of network. We now begin to introduce the application of the switch in support of Ethernet networks and the means by which traffic is managed that helps to generate multiple collision domains and isolate traffic flows. A key benefit of the switch comes in its capability to increase port density for a local network, meaning that more hosts can operate in the same broadcast domain whilst the potential for collisions is effectively eliminated. Interrupts to other end stations are also minimized, as we have demonstrated through ARP. However, in this instance, the behavior of the switch in this respect is highlighted. We start by considering three hosts in the form of host A, B, and C, each of which have an IP address that is part of the same 10.1.1.0/24 network, as well as a unique MAC address for the interface connecting to the switch. As a layer 2 device, the switch is only concerned with the MAC addresses of the host, whilst the IP address is only relevant to the end stations in this instance. The switch contains a table known as a MAC address table that is used to resolve MAC addresses to port interfaces. This should not be mistaken for the ARP cache table, which is used by end stations to resolve MAC addresses to IP addresses. A switch that is started for the first time will have no knowledge of any devices connected to the switch and must learn the MAC address information of peering devices, such as in the case of host A, B, and C. A populated MAC address table will be used to determine for frames received as to which interface the frame should be forwarded. This is performed to effectively reduce the number of port interfaces that the frame is transmitted out of and ultimately reduces broadcast behavior and end station interrupts. We see in this instance that host A has begun to forward a frame that is heading for switch A. The frame that has been broadcast is an ARP request and can be clearly identified due to the frame header containing a broadcast address in the destination MAC field of the frame header, and of course by the ARP header carried by the frame. The source MAC address of the frame is that of host A, and it is this MAC address that is used by switch A. Using the source MAC address and the interface on which the frame was received, which in this instance refers to interface gigabit Ethernet 0/0/1, switch A is able to record the path via which host A is reachable. As such, any frame in future that is destined for the MAC address of host A shall be forwarded via interface gigabit Ethernet 0/0/1. Since switch A has received a frame with a broadcast address as the destination MAC address, the switch is obliged to forward the frame via all interfaces, with exception to the interface on which the frame was received. We can see this occurring in this example here, in which an instance of the frame has been sent via interfaces gigabit Ethernet 0/0/2 and gigabit Ethernet 0/0/3. Since the frame is contained within the same broadcast domain, the source and destination MAC addresses of the frame remain unchanged. An instance of the frame is received by both host B and host C. However, the frame is only intended for one destination, which is not identifiable by the destination MAC address. The frame is decapsulated by both host B and C, and the ARP header is analyzed before it is determined that the ARP request is intended for 10.1.1.3 or host C. As part of the ARP process, an ARP reply is generated and the packet is forwarded back to host A. The source MAC address of the frame refers to host C and the destination MAC address to host A. The frame is forwarded by host C and received by switch A on interface gigabit Ethernet 0/0/3. As with frames received from host A, the switch will record both the source MAC address of the frame received and the interface on which the frame arrived, and populate the MAC address table with this new information. Following this, the switch must determine the forwarding interface via which the frame should be forwarded. It does this by identifying the destination MAC address entry in the MAC address table and the associated interface, which in the case of frames destined for host A is interface gigabit Ethernet 0/0/1. And so the frame is forwarded directly to host A over the gigabit Ethernet 0/0/1 interface in unicast fashion without any interruption to host B. Establishment of the switch as part of the Ethernet network may require that certain parameters be set. We show here a few of the common configuration parameters for the switch in terms of the negotiation mode that allows a switch to automatically negotiate the speed and duplex mode of a connection. Certain network interface cards of end stations may not be compatible if supporting higher speed connections, and where the switch interface is connected to a shared medium that may contain multiple hosts, a suitable speed and duplex mode need to be applied. Alternatively, the duplex mode and port speed can be manually configured through the duplex and speed commands respectively. This example shows how auto negotiation mode that is currently active can be disabled using the undo command, as well as how a full duplex mode and a speed of 100 megabits per second can be applied for the interface gigabit Ethernet 0/0/1. After the configuration changes have been made on the switch, we can use the display interface gigabit Ethernet 0/0/1 command to view the current status of this interface in terms of its current state, as well as verify that the changes made have taken effect. In this case, we can clearly see that the supported speed is 100 megabits per second and full duplex is supported, and that the auto negotiation has in fact been disabled. In summary for this section, then we just have one question here, and this asks, if a switch records the source MAC address of a host device on a port interface, and the physical connection of the host is then changed to another port interface on the switch, what action would the switch take? Well, from the point of connection, we would find that as the port is made physically active by the connection, a gratuitous ARP packet will be generated and propagated over the network, and then received by the switch that will proceed to update the MAC address table. When the connection is removed and the physical link is down, the connection loss will be detected and the MAC entry for that port interface will be removed from the MAC address table. Reconnection to another port will again initiate a new gratuitous ARP packet that is again received by the switch, allowing a new entry in the MAC address table to be generated.